Okay. Good evening, everyone. Hello, I am audible. Am I audible? Vijay Dharmapur. Okay. It is now 6:01 p.m. So we can wait more 1 2 minutes so that if anyone can join, then let we start our meeting. Screen is visible. Vijay, screen and sound are clear. Okay. Thank you. Thank you, Vijay. Okay, now I can start. Okay, first of all, I am introducing myself. Amiya Mandal. I am a PhD scholar and a BMRF scholar of IIT Roorkee, and I am working under Professor K.L. Yadav in Physics Department of IIT Roorkee. And here I am going to talk about the NPTEL course of course code MM31, that's Fundamentals and Applications of Dielectric Ceramics. I mainly do here the assignment problems. Okay. You already have done the week one I think you all have attended week one lectures by Professor Ashish Garg, who is the instructor of the course of IIT Kanpur from IIT Kanpur. Okay, so before I want to just introduce. I can see only one and Vijay Dharmakul. Okay, I just want to introduce Vijay Dharmakul. Okay, so can you hear me, Vijay? Okay, wait, please. Any problem? If you have any problem, you can type message in message section. Okay, just switch on your microphone and tell you where are you from and what are you doing, Vijay. Okay, then I will start. I think there is only one, two are there. Okay, Vijay, Vijay Dharmakul, can you hear me? Are you facing any problem in internet connectivity or screen showing from my side also or from your side? Any problem you can type message. Okay, okay, I am waiting. I am waiting, Vijay. I am waiting. Please try as soon as possible so that I can start my meeting. As as of now, I can see only one, so, so that I can start.
Hi sir, good evening. This is Vijay. Am I audible? Hello. 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 Sir, this is Vijay. Am I audible?
I'll start from here and can you hear me, Vijay?
Yeah, sir. Yeah, sir. Can you hear me? Hello.
Everything are okay or not? Please let me know.
Yeah. Everything is fine actually. Hello. Hello. Can you hear me? Hello. Is this audible?
Hello.
Hello.
If any problem persists, please tell me. Make me confirm first. Can you hear? Yes. Okay. Okay. Now we can start. I think Papa is there. And okay. Uh,
Hello.
okay.
Am I audible?
Vijay Dharmapur is still.
Yes.
So okay. Please respond.
Is
Please
this okay?
respond, please, so that I can start now.
Yeah, yeah. You can start now, sir.
Please do some response.
Not my audio is not visual, not up to you. I do one thing.
Okay. One is okay. Papa is okay. And okay. I'm waiting. Okay. Now we can start. Vijay Dharmapur can join the meeting. Okay.
Yeah, yeah. Is this
Okay.
audible, sir?
Please,
My side. Hello.
can you hear me? Please let me know. Yes. Okay. So can you briefly tell something about yourself, Vijay? Where are you from and what are you doing? Yes, I am. I can hear you. I can hear you. I can see you. But
Yeah.
I cannot hear you.
Okay.
Are
Okay.
you telling
Then I'll
anything?
speak.
I cannot hear you.
Yeah, yeah. Are you hearing me? Are you hearing me?
Yes, yes, I can hear. I can hear you. Bro.
Yeah, yeah, yeah. This is Vijay, assistant professor. DNR College of Engineering.
Okay, sir. Okay, sir. Are you a
Yeah,
student?
everything.
Okay, sir. Sir, sorry, sir. I
Yeah.
thought you were a student. So, okay, sir. Sorry, you are a student, sir.
No, I'm a scholar also.
Okay, okay, sir.
Recently, I submitted my thesis at my university, Adikavi Nana University,
Okay,
Rajahmundry,
from here, sir.
Andhra Pradesh itself.
Okay, sir. Okay. Okay, sir. So everything is fine now. Okay, I think everything is fine. Can I start now? Okay, so we can start now. So in week
Yeah,
one,
you
okay, you can put on your
can
mic on
in that course.
what?
Yeah, I was late to join actually that course, so I didn't submit week one also. So I need to clarify myself to join. So
Why?
I was late to register actually.
Okay,
So
okay,
I
no
didn't
problem.
gone through the rules
I,
lesson. Yeah,
I mainly do the assignment problems given to you for the week one
yeah,
only. Okay. So I
yeah.
just want
Okay, okay.
to solve the questions and solve the concepts. Okay. Uh, do not
Yeah,
solve one only. I want just clear the concept. Okay. So
yeah.
in
You can.
assignment problem, I am a PMRF scholar of IIT Roorkee, and I am doing
Okay.
here the NPTEL courses assignment
Yeah.
duty. Okay, teaching assistancy duty. Okay. If
Okay.
any
Okay.
question arises, you can write in message section.
Yeah.
Okay, this message section. Okay. Now you can mute yourself so that I can finally tell. Uh, I can finally progress. Okay. Okay. Thank you. Thank you. So, what have you learned in week one? Some basic introduction of the course. Courses fundamental and characteristics of dielectric ceramic. So, first you learned about the okay. Okay. So you have learned about the some week one course basic of crystal structure, basics of crystallography and bonding, arrangement of atoms. Okay. Let me some. There is some internet problem being facing in my Apple. So can you please wait for some time? Please
Yeah.
wait.
Okay. To have that issue, I think
Okay,
clouds are there in my area, so
okay,
the network is
okay,
unstable. So take it.
okay. Something is going not doing well. Okay, pencil is not working properly. So then just draw section, draw section. Just 5 minutes. Okay. You can mute yourself. 1 minute. Okay, is it now visible? There was some technical problem. Sorry for that. Okay. Actually, my screen was not working properly. So, okay, now, so basics of crystal structure. Basics of crystallography and bonding, arrangement of atoms in crystal lattice, structural formation, hardening solids. That's our discussed till now in this one course. So, we can now see to the question number one, which is really about the question number one is you can see that the ionization energy of hydrogen atom. So, how can we find ionization energy of the hydrogen atom? Okay, so hydrogen atom is mainly formed with a hydrogen atom with electron and the proton. Proton is situated at the center of the atom, yes, and electron is found at the at its center. Okay, so first of all, we can find the ionization energy. So what we mean by the ionization energy? Ionization energy is nothing but the energy required without the electron from its nuclear forces or the nucleus force. So here we can calculate the ionization energy of hydrogen atom from the Lambda expression, that is 1 by lambda equal to I into 1 by L1 square minus 1 by L2 square. Okay. So where R is the required constant and has the value 1.097 10 to the power 7 meter inverse. L1 is the principal quantum of the lower energy level. It is the principal of lower. Now, so here, if I want to remove the electron from its first cell of the hydrogen electron, so what we have to do? What we have to do? That put the value of L1 equal to 1 and put the value of N equal to infinity. So 1 by N square term it goes of 0, 1 by N square term will be 0. So 1 by lambda equal to R by N1 square equal to 1 only. Okay. So 1 by lambda is equal to R only. Okay. And C is speed of light here. If we know, so if we want to calculate the energy, we have to calculate H nu value. Okay. So from H nu value, we can calculate Hc by lambda. So put the value of H, which is 6.626 into 10 to the power minus 34, and just put the value of nu. Nu is nothing but C by lambda. C I know, and 1 by lambda value is equal to only R. Okay. 1 by lambda value is only R. So how can we take how can we write it? Okay, it is working. And okay, now so here N1 N1 equal to 1 and N2 equal to infinity. Okay. So for in hydrogen atom, we can see that we know that there is a plus charge present and an electron is surrounding its orbit. So if you want to remove this electron from this attraction force binding energy, Okay, so if you want to remove this electron from this cell to infinity, so N2 will be infinity, okay, N1 equal to 1. So here E equal to Hc into 1 by lambda, which is nothing but Hc into R, because this term will give you R value only R, only R. Just put the values H equal to 6.026, 10 to the power minus 34, C equal to 3 into 10 to the power 8 value, and R value is given as 1.097 10 to the power 7. 1.097 10 to the power 7. This will give you in joule. The value will give result in a joule value. So how can we get it in electron volt? You can see that option are given in electron volt. Okay. So if we want to find in electron volt, so what we have to do? We know 1 electron volt equal to 1.6 10 to the power minus 19 joule. Okay. So 1 joule equal to 1 by 1.6 10 to the power minus 19 electron volt. This we know. So just put this joule value into electron value. You can easily find 8 into 1.10 to the power 7 divided by 1.6 into 10 to the power minus 19. This will give you in electron volt unit. Okay. So it will find out as you can calculate. I am not going to use calculator or you can find it yourself, do it yourself. Okay. And you can easily get it. You can easily get it as a 13.6 electron volt. 13.6 electron volt. So the correct answer will be this. Okay. I think I have tried to find out the value of energy of the ionization energy value for the hydrogen atom. Okay. Hydrogen atom. Okay. Okay. So next we can go to the question number 2. Energy of 4 electron volt. 4 electron volt is equivalent to, okay, 4 electron volt. So 1 electron volt means 1 electron volt 1.6 10 to the power minus 19 joule. You have to just convert the electron volt value into joule value. It's nothing but the unit of energy. It is a unit of energy. Okay. So energy of electron, unit of energy. So 4 electrons is just multiply it by 4. Sorry. Just multiply it by 4. So you can see 6.4 into 10 to the power minus 19 joule. That is 6.4 into 10 to the power minus 19 joule. So it is a unit of electron volt joule. That's not the unit of energy. Unit of energy. Expression of energy is Q1 Q2 divided by 4 pi epsilon naught into R. So from here the Joule calculation that's all. So okay, we can go forward to the next question, question 3. Question 3, what is, okay, this is a energy diagram. This is a energy diagram. You have to find, identify curve A. There are three curves present. Curve A, curve B, curve A, curve B, and curve C. Okay, you have to identify the curve A. Options are resultant energy, repulsive energy between atoms, attractive energy between atoms, binding energy. Okay, so this is the curve energy diagram of which material? This is ionic solid. Ionic solid. This is the energy diagram of ionic solid. To understand this energy diagram, you need to know how ionic solids are formed. What type of energy? Repulsive energy, attractive energy, binding energy, what are those? What type of energy are there in ionic solids? And how they are formed, how they can act to form a ionic solid, they you have to understand. For this, we have chosen a sample, NaCl sample. Okay, we have chosen NaCl sample. So we can see here that we have taken NaCl. NaCl is an ionic solid, ionic crystal, ionic crystal. We can see that potential energy with distance curve is there. Okay, so what type of energy is acting here? What type of energy is acting here? If you read the theoretical understanding of this topic of how ionic solids are formed, you can see this term. This is a term to form ionic solid like NaCl, KCl. Okay, so where you can see that these two terms arises. This is called the attractive term, Coulombic attraction. Coulombic attraction. Okay, this Coulombic attraction. That is repulsive term. So Coulombic attraction term, here you can see NaCl is formed with N plus and Cl minus atom. N plus, Na plus and Cl minus atom. Okay. So at a large distance, they are separated. They are separated largely. And when the distance is getting closer, we can see that their potential energy is also increasing. So that is potential energy is also increasing. You can see this line, that is attractive interaction, E by R term. Here is a E by R term present here. So this, when radius is reduces, this term is increasing. This term is increasing. Okay. In which direction? In a negative potential. As you see, in the negative term arises from the potential energy term. Okay. So this term will increase, but how much it will increase? At this one, at this energy level. This is called binding energy, or bond energy. And this is called the bond length. Means at which bond they are forming this ionic crystal. Na plus NaCl, HCl, NaCl. So We all know about the Coulombic attraction term, which varies with radius. With decreasing radius, it is getting increased. Okay, but what about the repulsive term? So when this Na and Cl ions gets closer, then the repulsive energy repulsion between Na and repulsion between the which repulsion between the Na plus and Cl minus. Repulsion between Na and Na like charges and Cl minus and Cl minus. Okay. Due to Pauli's exclusion principle, you can, if you read some standard book, you can find this explanation of how repulsion energy works with this formula. You can see Pauli's exclusion principle, which states about that no two electron can stay in the same spin direction at one energy state. Okay, same energy statement. In one energy state, no two electrons can stay. Okay. There may be this. So in this way, energy level diagram will increase here. N1, 2, 3. Okay. So for this, the repulsive energy term can be explained from the Pauli's exclusion principle. So this term we can see that it is positive term and it is increasing with the internuclear distance. At very close, this is going to increase. So in result, so what is the resultant? In one way, there is acting attractive interaction, and in other way, there is acting repulsive interaction at a very low distance, in this distance. So what we can conclude? We can conclude that at a very low distance, at a particular distance, this distance you can find that at this distance, and this distance, the energy, there will be some binding energy where we can oppose this repulsion energy, we can get a static state where in ions can form, ions, solid can form with NaCl, NaCl. This situation and this type of resultant graph we can see. Okay. So this is a resultant graph. This is a okay, where energy is minimum. If energy minimum, then it will be stable. Okay. It will be stable. Okay. So that's also what will be the answer. Question is identify curve A. So the curve A will be resultant energy. We can go forward to the next question, that is question number 4. Question number 4 is, in the case of metallic bond, which is product 2. In the case of metallic bond, which is product 2. So metallic bond, in case of metal, how metallic bonds are formed? We know about metal. There are free electrons at the outer shell. Okay. There are free electrons at the outer shell. Large number of free electrons are there. So they form an electron cloud there. Okay. So we know about that, and so there are 4 objects. They are directionally neither near, they are not directional. Directional at least. Directional mainly dipole direction, but there are no dipole option is the value of the bond energy. Most metal lies between 50 to 350 kilohertz per meter. Okay, so we can see this statistical diagram of bond energy temperature. If we have considered the temperature, we can see that for metallic bond, energy lies between this region. Although this is varying with temperature, so if we get it at room temperature means 27 degrees centigrade, 300 Kelvin. Means at that point, we can see that it is lying between this region. Okay. It is lying between this region. So from the answer, we can see that 50 to 350 kilograms it is lying. So this is also correct. Option B is correct. The value of the bond energy lies between attokilojoule per mole. So B option is correct. And they are caused by the sea of free electron. Okay. So this option is also correct. As metals are consist of electrons. Okay. So this option is also correct. They are caused by sharing of electrons. No, sharing of electrons is done in which covalent bond. It is not a covalent bond. Okay. So the directional is not seen in ionic in metallic bond. Okay, it is seen in dipolar moment type bond. Okay. So, and what about the van der Waals? Van der Waal is where the dipoles are present in very weak. Van der Waals shows vibration of dipoles. So, okay, this I'm not going to tell about. And so these types of bonds are present, covalent, ionic, metallic. We are interested. The question is about metallic bond. So metallic bond lies out this bond energy length, and uh, it is C of free electrons. So what will be the answer? Final answer. Final answer will be B and C. Final answer will be B and C. These two. Okay. 1 minute. We can go to the next question number 5. Bond energy in ionic solid increases as bond energy in ionic solids. We have seen in NaCl case at this graph. So bond energy increases for which number of ions increases, Madelung energy increases, change of charge of ion increases, melting temperature increases. Which option will be correct? We have to we are now going to find number of what is the rule of number of ions in the bond energy of ionic solid. Ions means if we take the sodium chloride here, so what will be the ions here? Sodium ion, chlorine ion, and their corresponding electrons. Okay, so these are the ions in sodium chloride solid. So how the effect in bond energy? Anodhu is So how they affect in bond energy in ionic solid? So there are number of ions, that is sodium, chlorine, electrons are present in this structure. This is the structure of sodium chloride, where you can see this is sodium. Sodium is red. There are sodium, which is denoted as green color. Okay. So we can see, if we can see that this chlorine atom is surrounded by 4, and 5, and 6. Similarly, sodium atom is surrounded by 6 atoms, chlorine atom is surrounded by 6 atoms, iron is surrounded by 6 ions. So 6 neighborhood are there. So that is highly structural, okay. Highly structural, and each are similar to, each atoms are similar to each other. Highly structural, highly periodic. This is also periodic in nature. Means if we repeat this this portion also, we can repeat. If we repeat this portion, we can form the total NaCl crystal. Okay. So highly repeatable. So what about the bond energy? For this, you have to know the bond energy. How do you find the bond energy in the metal ionic solid? Okay. So the expression of bond energy you have to know. Okay. So this is the expression of bond energy. Or why we have taken? Because if we take n number of NaCl, then how will be ions? Ions will be 2n numbers because of n number of Na plus n number of Cl minus ions. That's why we get 2n. That's why if we want to calculate for one ion, it may be sodium and calculate. I am not going to discuss in details. You can find this expression in any standard books. I just want to tell what is the effect in energy. If you go forward, this relation we can see this term, this is attraction term, this is repulsive term. Attraction term involves alpha value. This alpha is called the Madelung constant, which consists of, sorry, this is not. Only this alpha is called the Madelung constant alpha in the energy term. And this is the uh, this is the attractive energy term in a band, and this is the repulsive energy term. So both are involved in for the formation of ionic solid. Okay. Now you can see. Okay. So what terms are involved here? We can see that if we take this color, this term is involved here, and this term is involved here. Two terms. They are told as what? Charges of electron. Charges. And this is Madelung constant. Madelung constant. This term is termed as a Madelung. So now, if we go, so bond energy in ionic solid increases. How do we increase the bond energy? Number of ions, we will see. This Z signifies what? Z is telling about the number of ions. Z1 is the type of ions. So this is a type of ion. This is sodium ion. So this is the type of ions. So number of ions. So number of ions are involved here. And so number of ions are fixed. Charges of ions increases. Okay. Number of ions, sorry. Sorry, number of ions in number of ions in the state. That one is the number of proton. This is not number of ions. So number of protons and number of electrons. So this term and this term are what terms we involve in binding energy. So what will be the difference? Charge of ions greater than constant, greater than negative than then both this both constant. And you can see that in every problem, not only option can be correct. There may be multiple options, these can be correct. Okay, that's you should have to mind keep in mind. Okay. So the effect of Mendel energy also involving on energy, effect on change of ions also involving on energy. So that's all for binding energy on energy of the atoms. Now we can go to the question 6. Okay. In C, the question is okay, question number 6 is why are the cations and anions in a sodium chloride do not collapse, into a random ensemble of sodium and chlorine. So in a random ensemble of sodium and chlorine, there they are present in they are present in what will happen? They are highly attractive in nature. So high attractive energy will be there. Okay. And repulsive energy will be there. Because this in instead of sodium chloride, repulsive energy will be there. But it will be decreased as we have seen in the in this graph. As sodium chloride for the repulsive energy will be decreased, increase after a certain point, but as a result, it will stable. For the cumulative of I have previously discussed about NaCl and its energy. Cumulative effect of attractive energy and repulsive energy. Rise to try to optimize or minimize the potential energy in the system. Every material wants to try to stay in the lower energy state. Okay. So here sodium chloride also want to stay in lower energy state. In a random ensemble of sodium and chloride, sodium plus minus random ensemble sodium chloride, there will be high attractive energy. So high Coulombic attraction energy will be there, high cohesive energy will be there. Repulsive energy must be decreased. You can see that repulsive energy here is decreasing. Okay, this is the repulsive energy, but as a result, we can see that as a result it is decreasing when attractive energy comes to play in repulsive energy interaction. So decrease in repulsive energy, this is also correct. But in result, what will be the final result? Because of everything, every result, lowering of potential energy is, so everything will be done and lowering of potential energy will be effective. Okay, so it will be effective. Final result will be this. So they all involve to lower the potential energy. So what will be the final answer? Final answer will be not all three, not ABC. Final answer will be the what is the cumulative effect and what is the result? Final result. Final result is to lower the potential energy. Final result is to lower the potential energy. Okay. So random ensemble always try to lower the potential energy. Okay. Okay. Just read this question. Try to understand and in that time I just want to take some water. Okay. So what will be the radius of cesium and chlorine? Hmm. Radius of cesium and chlorine, which is following lattice constant. Okay. Try to understand the question first. That radii of chlorine, cesium, and chlorine. Are everyone present here? Okay. So the question is the radii of cesium and chlorine are R1 and R2 respectively. Which of the following is the lattice constant of crystalline cesium chloride at room temperature? So to find the lattice constant of crystalline cesium chloride in at room temperature, cesium chloride always shows the crystallinity behavior without shifting any atom at its position from its position. So you can see this type of structure, this type of structure, this type of structure of cesium chloride at room temperature. At room temperature, highly periodic. So to find the lattice constant, that is A, what we have to know the crystal structure of cesium chloride. How cesium chlorides are arranged in a crystal. So again, this is the unit cell of cesium chloride. This is the unit cell. The unit cell of cesium chloride consists of, this is the chloride atom. This is the chloride ion. And this is the cesium. So it's noted here. Cesium plus and chlorine ions. We can see that it is just looking like a body centered, but not body centered. In body centered cubic, in body centered, all atoms are similar. But here, cesium and chlorine are different. Chlorine is situated at each corners of the unit cell, at each corners of the unit cell. But cesium is situated at the center of the unit cell. We can also think this, and cesium can also present at the corner also. At the corner also, and chlorine can also present at the center. So they can be exchanged vice versa. Okay. So it can be shown, it can be seen as one chloride unit cell. Chloride unit cell. Unit cell is penetrated into cesium unit cell. Okay. It can be seen, it can be understand is like that. That chloride unit cell has been penetrated into a cesium units. Okay. So this type of unit cell is formed in cesium chloride. Okay. So if you know this type of structure of cesium chloride, we can easily find the value of lattice constant. Lattice constant. Okay. So how can you find the value of lattice constant where R1 and R2 value is known? So if we look at this plane, at this diagonal, at this diagonal, if we look at this diagonal, okay, this is A and this is R1. So what will be the length of the diagonal? Length of the diagonal is root 3 into A. This is simple geometry, you all know. Length of the diagonal of a unit cube is root 3 into A. And what do it involve? The radius of cesium and the radius of radius of chloride atom. And it will be just R1 and this will be R2. Okay, this will be R1. So what will happen? R1 plus R2 plus R2 plus R1. This is giving you R1 plus R2. We need just a simple calculation. Just you have to know what are the position of cesium and chlorine. Okay, this is the calculation and this is the answer. So 2 root 3 R1 by R. Okay, so this is the calculation. This is the diagonal length, and at the diagonal, uh, one page of the cesium atom is involved there. So only the radius R1 will be there, and full radius of full diameter of the cesium atom is there, and the half radius will be there. Okay, so this will be the answer. Okay. We can go to the next question, that is question 8. What would be the distance of estimated in a simple cubic structure? A simple cubic structure distance of nearest neighbor in a simple cubic structure if R is the radius of it. Okay. Distance of the nearest neighbor. So I have illustrated some. This is a typical simple cubic unit cell. Okay. It is simple cubic unit cell where these are the body, these are the length of the unit cell, and R is the radius of atoms situated at each 8 corners of the unit cell. Simply, the unit cell is formed with 8 atoms Also, simply you can find it also 1, 2, 3, 4, 5, 6, 7. Okay. This is the simple structure for listing. And if we reduce the size of the atoms, we can see the relation is like this. So, what will be the distance of nearest neighbor? If you consider this atom, the nearest neighbor is this. Everyone are situated at a distance A. Okay. So, what will be the distance of nearest neighbor of simple cubic unit cell? Everything are A, so we have to find the value of A only. We know the value of the radius. If we increase this, we can see that the radius is R1. I'm sorry, they are similar atom. Okay, they everyone are similar atom. So they are here also. So what will be the nearest neighbor in terms of value? It's going to twice that. Okay, this is very simple. You can easily calculate. The nearest neighbor distance is 2r, where the simple cubic structure is r. R is the radius of the atom. Okay. So that's question number 8. This is very easy. Okay, we can go to the next question number 9. The number of lattice points. This is a very important question. The number of lattice points. Lattice points. Don't be hesitated with not atoms. This is not atoms. Lattice point. There is a difference between. They are different. Atoms and lattice points are different. Okay. So don't confuse with lattice point and atoms. So the number of lattice points in the primitive unit cell. Primitive unit cell. What do you mean by the primitive unit cell? Of the HCP structure, everything, many things are present in the HCP structure. What do you know about the HCP structure? HCP means hexagonal closed pack. Hexagonal closed pack. Okay. So what do you mean by the primitive unit cell? Primitive unit cells are those. So the unit cell, what do you mean by the unit cell? Unit cell is nothing but the smallest possible volume. But the primitive unit cell is those every lattice point must be and belongs to the at its corner. We will discuss about that for HCP only. So the effective number of lattice points in the primitive unit cell will be 1. Every time effective number of primitive unit cell will be 1. So from here, from this point of view, you can easily say answer will be 1. But I just want to explain something about the HCP unit cell, hexagonal closed pack unit cell. This is the three-dimensional figure of hexagonal unit cell. You can see that 1, 2, 3, 4, 5, 6. Okay. In this phase, 7 atoms are there. They have been reduced, the volume have been reduced to understand further. Okay, so this is layer 1, layer A. This is called layer B. Okay, this is called layers A. Every atoms of layer B are at their void position. Void position. Okay, there are 3 atoms. Three atoms are there in layer B. Okay, three atoms are there in layer B, B, A layer. Okay, so this type of structure is seen in HCP, that is a unit cell. But what about the primitive unit cell? We just want to see the primitive unit cell. You can see that the unit cell and the unit cell of the HCP lattice, we can, if we cut the unit cell, this portion, if we cut this portion, cut out this portion, only this portion, taking this atom also, and this four neighborhood of this atom, we can see the similar arrangements are also there here. For here also, similar arrangement are there. So there are three this type of arrangements, three types of arrangements. Means are there. So if we repeat this three times, we can repeat full unit cell. So if we cut out this portion, we can see that this type of arrangement in the hexagonal closed cut layer, where 8 corner atoms are there and one center atom will be there. There are three center atoms, each contributing this type of structure, so that we can form, if we multiply 3, we can form this type of unit cell. Okay. So we can see it as a primitive unit cell. Primitive unit cell. In primitive unit cell, what are the lattice points? One, lattice points. Lattice points are there are 8 lattice points at each corner. Lattice points always situated at each corner, which are sharing at 8 neighborhood cells, cubes. So what will be the effective number of lattice points? Effective number of lattice point is 1. Effective number of lattice point is 1. Lattice point. Okay, so effective number of lattice point is 1, not atom. Not atom. Okay. If we consider the atom, so atom, how many types of atoms? One at corner, one at center. At corner, one at center. Okay. Okay. I think I have tried to understand this portion. It's a very important question. So, what will be the lattice points? Here, this will be the answer. Okay, one lattice point. Then question. Nine. Okay, so there are total 15 questions. Then now go to the question number 10. Okay, R is the radius of an atom of a PCC structure. What will be the maximum size of interstitial space? Sphere. That can be just fit into the void between two body centered atoms. Okay. So if we try to understand body centered atom, so So, okay, we can see that at body centered atom, for body centered atom, so at each corner there should be atoms as well as at a body. So if we draw another, body centered atom, we can denote this as this. Okay. This is the body centered atom. So these are the body centered atom. Body centered. Okay, this is also the body centered atom. The radius of the BCC structure of every atom is R. And the question is, what will be the maximal size of an interstitial sphere? Okay, just fit into the void between two body centered. Two body centered atom. We have just fit an atom in this void. Okay, let's say the radius of this void is capital R. Okay, capital R is the radius. We have to find the radius. Okay, so what will be the distance between these two? That is, this is at a distance a by 2 because this is total is a and this is at a distance a by 2. So the total distance is n a. Okay. So, and if the radius of the atom is r, then what will be the, and if the radius of the r, then what will be the replacing using sorry. Okay, let's fill the body center atom. So what is the difference between this? Let's change to a. Sorry, this will not be a. This will be 3 into a. Okay, this will be 3 into a. Atom BCC structure, maximum size of the it's the body center sphere. Just fit into the body center atom. So the distance will be 3 into a. Stepwise r plus r 3 into a. 3 into a is the diameter. So just half gives you say like sorry minus twice half. This is the okay. So there will be this here answer. Maybe there is some mistakes in here. Interstitial scale. Okay. I have to look into this matter. So maximum size of an interstitial radius of an atom for BCC structure. Okay. So what will be the BCC structure atom? This will be this CA equal to this 4R. Root CA equal to 4R because 3 atoms are present in there. So R will be presented as root 3 by 4 into A. So this will be the root 3. You have to use root 3 into 4R. This equation and sorry, this is 3A. And you have to use this 2 and you will get the value as this. Okay. So you can just write it. In terms of R, we have to find the value. So what will be the A? A will be here 4R by root 3. Okay. So if we cut out 2, so 2R by root 3 will be present there. 2R by root 3 will be present there. So we need to find the value of R. So R will be there 2R by root 3 minus R. So if we take 2 by root 3, yes, okay, that will give the value of 1. Okay. So where do I find this relation? Where do I find? If we can see the body-centered atom, body center, this is R, this is 2R, and this is R. So 4R. Total gives you 4R. And what is this is A, and diagonal distance will be root 3 into A, equal to 4R. So there I will get a relation, and this is the interstitial side relation. This will give A value, total distance, as I have previously discussed. That is A by 2. That is A by 2. Okay. So this gives total distance as A. From this relation, we will get this relation 2 root 3 by minus 1. So the correct answer will be this. Okay. Okay, we can go to the next question, question number 11. Okay. 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 Question number 11 is which among the following, which among the following means this 4 option 1, 2, 3, 4 is our closed packing arrangement. What do we mean by that? Closed packing arrangement of atoms. Considering each layer is closed packed in 2 dimensions. Each layer is closed packed in 2 dimensions. Okay. Each layer. Okay. I have shown a layer here in 2 dimensions. What is the layer? A balls. A balls have been denoted as this. These are the A balls. A atoms. They are closely packed. Whatever we can close, we have done the close pack here in this package. So A layer is there, B layer is there. Now, if we want to introduce B layer, then what? In which we introduce the B layer. There you can see the void at this level. So here, if we use the B atoms, you can place the B atoms in this level. The void will be closed. Okay. If we one second, void will be closed if we place the B atom at this level of, don't confuse with the level. This level and this level are different. Okay, so I have closed this void so that we can form closed pair. How we can form the closed pair? By filling this void. By filling this void. Okay. So I am filling this level of void with B types of atom. And this level of void, there are, you can see, okay, there is also a label. This is different level. Okay. So I am filling this level with C types of atom. C types of atom. Okay. So similarly, in the upper level, we fill C atoms. In the lower level, we fill B atoms. C atom, C atom, C atom, C atom, B atom, B atom, atoms, B atoms. We have filled it C atom, B atom, C atom. Okay, don't confuse with color. I have shown in color B and C. So in this way, we can fill those voids. Those voids. Okay, we can fill those voids. But how can we arrange those voids? Why I have taken B, B, B? Why I have taken C? Why I have not taken A? If we fill A atom with A atom, means at the place of A atom. If we place at the place of A atom, then voids will be present there. Then what will be the meaning of the closed packing? So we cannot place similar atom A, B, B, C, C. We cannot place similar atom. We cannot place similar atom as we need to fill the void for closed packing. Okay, closed packing. Okay, so we have seen that we placed A, then we must have to place B or C. We cannot place A. Then above B or C, we have to place C or A. So in this sequence, it will go. If we arrange A, B, C, then it will go as A, then B, then C. It will go as clockwise sequence. Clockwise sequence. Okay. This is the diagram. Stacking sequence. Stacking sequence is closed path. First of all, A layer was there. Above A layer, we have put it B and C, not A. Okay, if we put A above A, then there will be no meaning of closing the voids. We cannot put A on the A. So we have put it A, we have put it B above B and C. After B, we can put C, and sequence will be B after C. So B will be C and C, then A, then will be A. And if we put C, then what we can put above C? First of all, we put A, then we put B. First of all, we put A, then we put B. Similarly, this sequence will go through. There's an important line. Any sequence of A and B and C which avoids AB, BB, CC gives us a closed pattern. So we have to avoid this in the 3D scale. Okay. So what will be the, we can see the option now. What will be the option for the closed packing system? A A, B, that is correct. After B, A can be there, that is correct. B is also B can be correct. B after B, A can be correct. B is also correct. So this is correct. Above A layer, B is possible. Above B layer, C is possible. Above C layer, A is possible. Above B layer, A layer, B is possible. Above B, C is possible. Above C, A is possible. Above A, B is possible. Above B, C is possible. So this layer is also be possible. Okay. Above A layer, B is possible. A is possible. B is possible. C is possible. D is possible. C possible. A possible. B possible. C possible. This layer is also possible. Above C layer, above A layer, C is possible. But above C layer, C is not possible. So it cannot go forward. So this level cannot be true. So the answer will be clear. Okay. Question number 2. What will be the packing efficiency first? Packing efficiency. Packing efficiency means volume to volume is occupied, number of atoms occupied, divided by occupied by the atoms, divided by total volume. That's the packing efficiency of this term. What's the this? We have to find it. Having an interstitial atom exactly fitting in the body center. Okay. So we have to fit an interstitial atom and the body center. Okay. So what will be the what will be the okay. So these are the experiments of a simple unique unit cell where every atom is represented at each coordinate. So that is the nice for unit cell. And what we have to do, we have to put an interstitial cell at this interstitial cell. And after that, we have to find the packing efficiency of the symptomatic crystal. So, we can see this diagram. And interstitial site is symptomatic crystal structure. This is the interstitial site shown in this color. If we reduce the reducing the atoms here, the atoms have been shown here. So this is the interstitial site. Okay. So what is the packing efficiency of the interstitial site? So occupied volume itself and total volume by itself. So total volume of the itself will be A cube. Okay. And what is the volume of the 8 atoms? Volume of these atoms. So what is the volume of these occupied atoms? We can see that here we can see that this is A and this is R. And add the diagonal for diagonal distance. This is root 3 into 8. We have to find this diameter of the interstitial site. What will be the diameter of the interstitial site? Root 3 twice R. Diameter of the interstitial site is R, say. Okay. So, R R plus R gives you root 3 by 2 and twice r equal to also a. So r equal to a by 2 or equal to root 3 a by 2 minus r means a by 2. A by 2. So what will be a by 2 root 3 minus 1 will be r value. Okay. And if we find the value, we can see that root 3 value of root 3 is 1.732. So, okay. So, R value we have found out in this way. Okay. So, there is a one atom of one each atom situated at 8 corners. So, effective number of atom is 1/8 of 8 is equal to 1. Situated, so, two atom at the interstitial side, there will be 2 atoms. So, the volume occupied by each atom will be 4/3 5 r cube plus 4/3 5 small r cube divided by a cube. Okay, packing efficiency. So 4/3 5 4/3 5 capital R is this. So a cube by 8 into root 3 minus 1 cube plus 4/3 5 twice a equal to r equal to a by 2 means a cube by 8. Okay, divide by a cube. By omitting a cube from each side, we can see that 4 pi by 3 into 8 will be common and root 3 minus 1 cube plus 1, this will be the final value. Okay, if we find the value, so pi by 2, so this will be pi by 6. And if you find the value, you can find the value as 0.73 like this. Okay, 0.73 like this. So the packing efficiency is always calculated into 100%. Okay. So this is just like body center cubic efficiency. Okay, I am just trying to find out the value of just 1 second. 5 by 6 root 3 minus 1 is root is this is giving us 1.39 into 12, 6, 0. So this is 0.729. It is 1.39. It's giving you. Okay. Okay, everything is fine. So this is the packing efficiency, and the answer will be 0.73. Okay. Question number 13. The size of the largest sphere that can be fitted at tetrahedral interstitial site of nickel would be tetrahedral largest sphere that can be fitted at tetrahedral interstitial site. What would be the tetrahedral interstitial site of nickel? So you have to know the initial structure of nickel and tetra. What is the meaning of tetrahedral? Tetrahedral, we have to know this, and after that we can find. So this is the basic characteristics of nickel. Nickel, the chemical is this, and this is a FCC crystal. This is FCC crystal. You can see this type of structure where this is the this is the length of the crystal. Now is the radius of the each atom, and in for crystal units, that is phase, that is a very that's nickel. It is called nickel. Okay. So according to tetrahedral site, tetrahedral right side. Okay. So this is the FCC initial. This is the FCC initial. Okay. This is the FCC initial. You can see that at each phases of initial, there is an FCC initial along with it is formed. So this is the FCC initial. Because you are familiar with that. What is the determined interstitial site? Okay. Determined interstitial site is like three atoms are there. If there are three atoms situated like that, and at this white point, if you situate, if you position another atom of this, so this will look like this will form a pyramid-like structure. Tetragon. So tetragon, tetragon is four. One is place. Okay, so four times we get that this can, and there will be three planes. This, and this, and this. Okay. So from this concept, tetragon has been given. So what do we know? Tetragon of right side. It is FCC crystal. FCC crystal. We can see that this face-centered atom, this face-centered atom, this face-centered atom, and a corner atom is forming a tetragonal-like structure. Okay. How? Means if we increase this, if we increase this atom, and if we increase this atom, nearby three face-centered atom is for, and we are placing this corner atom at the middle, just like this. I have shown you. So this is forming a tetragonal fluoride. Okay. And the red symbol is the interstitial site. Okay, red symbol is the interstitial site. We have to find out the volume of this red, and we can find from each corner. So there are 8 corners. So we can find 8 tetragonal voids. Okay. So this tetragonal void forms a cube of length what? Of length a by 2. Okay. So we have to find out this radius of this atom. So we know the radius as r. Okay. Radius of each atom is r. So what will be this? Root 2n twice r. This is a relation. And from this relation, we have this length, root 2n twice r. And this atom is situated at the body diagonal with this atom. So it will be the half. This will be a by 2 because this is a by 2. Okay, if this is a, then it will be a by 2. So root 2 a by 2 equal to gives you twice r. And what will be the diagonal length? Diagonal length is root 3 a by 2. Okay, diagonal length is root 3 a by 2, which is nothing but twice of which length? Which is nothing but twice of uh, capital R, that is for interstitial, that is for atom. Okay. So using those two relations, this is a relation and this is a relation. 2a by 2 equal to twice R. Using two relation, after omitting small r, omit it. Omitting small r, we can get the value of capital R in terms of A. Okay. And if you try to find out the value, okay, if you try to find out the value, you can see that from here we can see R as root 2a by 4. Okay. So a by 2 root 2. And putting the R value here, I will put letter. So R, capital R will be root 3 a by 4 minus small r. Okay. So root 3 a by 4 minus r means a by 2 root 2. Okay. Just put the value of a. It will be turns out as nearly 3.3, nearly 0.3. Yeah, okay, I am not going to calculate it. You can do yourself. Okay. After putting value of a, and this is a value problem, and you can see the answer will be 0.34. Just understand the concept of this topic, and you can see this figure. How this is a by 2, this is a by 2. Okay. And so these are not important. So this is a by 2. Okay. So how a by 2 and r is related? R is here, the atoms of the radius of the atom, and this is the interstitial site. This is the interstitial site of the tetragonal voids. Okay. Tetragonal site. Red is tetragonal site. Okay. Tetragonal void. Red is tetragonal. Okay. So I have calculated the value of R from here. We can see the value of R. Put the value, and you can get the value as 0.34. Okay. Now we are going to question number 14. Okay, this is not octahedral values. We are not of octahedral value situation. This is a tetragonal void, tetrahedral void. Again, tetrahedral void for primitive HCP unit cell. Number of tetrahedral void. So, we have seen the primitive HCP unit cell as there will also be, okay. So this is primitive unit cell where the center there is present. And we have seen that, and this has been cutted out from this section, where one is atoms present there in the HCP unit cell. So this is the primitive unit cell where you can see that the tetragonal void present. How tetragonal voids are formed? This atom forms a tetragonal void with these three atoms nearby. So there is a tetragonal void formed. There can be with taking this, we can form tetragonal void this in this position. And taking this atom, we can form that tetragonal void at this position. So for this type of, but for this atom, for this unit cell, how many tetragonal voids are present there? There are four tetragonal voids. You can see that there may be, or just take this, what this? Okay, understand this. Just take uh, this unit cell, this unit cell. You can see that there's a void present, tetragonal void present for this unit, for this atom. Okay, magnetic is equal to, you can find a tetragonal void at this point. So for this case, we will find actually this point, this point, this point, this point. So determine first one, and for each data point, one for this side, one for this side, okay, and for each edge cell, development provides there will be four columns, four, four for each atom, which is sharing four neighborhood. So we can get two. So 1 plus 1 plus 3 equal to 4. Four determinant points are presented. Determinant points are can be determinant point. So this, 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 and this. So finally, this four. Okay, so there is four determinant point in primitive units. Okay, we have reached 40%. There are only 1% left. 50 number question. What is the fraction of octahedral void? Okay, I am saying. Okay, now time is 5, 7, 53. Time is up to 8, 2 hours time. Okay, and now 7 minutes are there. Okay, I just let this question and I will start it. So, what will be the fraction of octahedral void is given by aluminum ions in aluminum? L Kochi, where ratio of the aluminum, radius of aluminum, cadence, L G plus, oxygen minus, is 43. Means reducing oxygen's mass determine aluminum. Okay, then this case. So oxygen will pass bigger. So what will be required? Octahedral voids. We have shown here a schematic diagram of octahedral void, where you can see that four atoms are present at each core at these points, and Above the middle void section, above and below the middle void section, two atoms have been placed. Okay, so we can form this as a tetrahedral void. And where the void will present? In this case, in this place. This is called octahedral void. Octahedral means 8 planes. This is a plane. In upper place, you can see the 4 planes, upper 4 planes, and at lower, there will be 4 planes. Okay. So that's why it is called octahedral void. And this is the another arrangement of octahedral void. Just it rotated, it rotated in an angle, and you can see at the upper surface there is 3 atoms are situated. So that is 1-4-1 arrangement, and that is 3 by 3 arrangement. Okay, 3 by 3 arrangement. So above the above layer, 3 atoms are there, and the below layer, 3 atoms are there. So this is the structure, and at the middle there will be a void. This is called the octahedral void. Okay. So there is a schematic diagram. You can see in HCP crystal, in HCP, okay, Al2O3 forms HCP structure. So how octahedral voids are forming here? If you see this structure, here 3 atoms, 3 by 3 arrangement. Okay, and this octahedral voids are present, is present here. Okay, so how many octahedral voids are there? 1, 1, 2, 3, 4, 5, 6. 6 octahedral voids are there in a HCP lattice. Only HCP lattice, not, but what for alumina? Due to the radial structure of alumina, sorry, we can find Al2O3 alumina except fluoride. Okay, where you can see alumina is situated at the octahedral position. Okay, at the octahedral position. But how they are contributed in the octahedral position, we can see it here with better. Only 2/3 of the total 6 octahedral sites. This is very important one. Do not cover the all sides. Do not cover only 2/3 octahedral position. So there is 6 layer. This layer contributes 6 of 12, and these 2 layers contribute 1 by 6 times 12 carbon, and face contributes 2, this and this, and these 3 contribute 6 totally. So total 6 atoms are there. So 6 of 2/3, that gives 4. 6 of 2/3, that gives 4. 4 void. Okay, 2/3 of the octahedral sites will be there. So what will be the ratio of aluminum oxygen? 6:4. So what is the question? Question is the fraction of octahedral void. So 2/3 of 6, that gives you 4. So what is the fraction? Fraction is 4 up to 6. That is 2 by 3. That is 0.667. Okay. Okay. So that's all. I have tried to understand you all the questions. Okay. Now it is already 7:59 p.m. I have tried to finish within the time, and it is for 2 hour assignment. Okay, I think I have tried my best to understand. And any question? So it is right. Thank you, sir. Thank you, sir. Thank you. Thank you, sir. Thank you. Thank you. So we can leave, end the meeting. Can we end the meeting? Good night. Good night. Good night. Good night, sir. Okay. Okay. See you next week. See you next week, sir. Okay. Okay. Just ending the quiz session.